Welcome to the Deep Sleep Science channel. Tonight, we're traveling far beyond the familiar glow of the Milky Way toward a region of the universe that feels almost impossibly quiet, the Boötes Void. It isn't a hole you can circle on a photograph, and it isn't a supernatural emptiness. It's simply a vast stretch of space where galaxies are much rarer than normal, like a thin patch in the cosmic web where the usual glitter of distant islands of stars fades to almost nothing. The Boötes Void lies in the direction of the constellation Boötes, but it's not inside the constellation the way stars are constellations, are just patterns on our sky. This void is hundreds of millions of light years away, and it spans hundreds of millions of light years across. On scales like that, you're not talking about a single object. You're talking about a whole region of the universe, a gigantic volume where, compared to the cosmic average, there are far fewer bright Milky Way-like galaxies. So what is it, really? In astronomy, a void doesn't mean empty. It means underdense. The Boötes Void still contains dark matter, thin gas, background radiation, and even some galaxies. But the galaxy density drops dramatically compared with surrounding space. Imagine the universe as a three-dimensional spiderweb, bright threads and knots where galaxies gather into filaments, sheets, and clusters, and between them, large bubble-like spaces where matter is spread thin. The Boötes Void is one of the most famous of those bubbles, sometimes nicknamed the Great Nothing, simply because its scale is so striking. How did something like this come to exist? The short answer is gravity working patiently for billions of years. In the early universe, matter was almost uniform, but not perfectly. Tiny differences in density, seeded in the earliest moments, acted like a blueprint. Where there was a little extra matter, gravity slowly pulled more in, building filaments and clusters. Where there was slightly less matter, gravity had less to grab onto. Those underdense regions expanded a little faster than average as the universe grew, and over time, matter flowed outward toward denser structures. The result is a natural foamy pattern, walls and filaments outlining large, underfilled interiors. Voids can also grow by merging smaller voids coalescing into larger ones as the cosmic web shifts and evolves, which is one reason truly enormous voids are possible. And how did we find it? Not by seeing a black patch in the sky, but by measuring distance. In the late 20th century, astronomers began building 3D maps of the universe using redshift surveys. Redshift is the stretching of a galaxy's light to longer wavelengths. As the universe expands in general, the larger the redshift, the farther away the galaxy is in the Hubble flow. When researchers like Robert Kirshner and colleagues surveyed galaxies in that direction in the early 1988, they noticed something surprising. Over a large range of distances, the galaxy counts dropped sharply. In-wedge plot diagrams showing galaxies by angle and distance the Boötes region displayed a dramatic gap. Follow-up redshift measurements confirmed that it wasn't just a missing patch of data, the underdensity persisted across multiple sightlines and sampling methods. What makes it even more fascinating is that the void didn't stay empty in the simplistic way early headlines suggested. As surveys improved and astronomers searched in different wavelengths, they began to find more galaxies inside, often faint, gas-rich, star-forming systems that are easy to miss in bright optical catalogues. Infrared surveys could reveal dusty star formers. Radio observations of neutral hydrogen could uncover galaxies with lots of gas but little starlight, and emission line searches could flag compact galaxies actively forming stars. So the Boötes Void became a perfect lesson in how discovery works. First, you see a dramatic pattern, then you test it, refine it, and deepen it until you're not just saying nothing is there, but understanding what kind of environment it truly is. And that environment is scientifically valuable. Void galaxies help astronomers study what galaxies do when they're not constantly being disturbed by crowded neighbors. They offer a calmer laboratory for separating a galaxy's internal evolution from the intense nurture effects common in dense clusters, like stripping and repeated close encounters. Voids also matter for cosmology itself. Their shapes, sizes, and the way matter flows around them respond to the universe's expansion history, meaning voids can be used carefully and statistically as another way to test how the cosmos has evolved. So as you listen, you can picture the Boötes Void not as a scary emptiness, but as a quiet, oversized cell in the cosmic foam, a place where the universe's structure is revealed just as much by what's missing as by what's present. The Boötes Void is an enormous underdense region of space, seen in the direction of the constellation Boötes, where galaxies are far less common than in surrounding areas. Astronomers often describe the Boötes Void as roughly spherical overall, which means that, on the largest scales, it resembles a giant bubble-like region of low galaxy density rather than a thin gap or a narrow tunnel. The center of this void is commonly given near right ascension 14 hours 50 minutes and declination about plus 46 degrees, which is simply a sky coordinate addresser telling observers where this emptier beat region appears when we look outward from Earth. The Boötes Void was recognized through galaxy redshift surveys, meaning astronomers didn't see a literal dark hole in a photograph, but instead noticed that the usual sprinkling of distant galaxies was missing when distances were measured systematically. Robert Kirshner and his collaborators reported the Boötes Void in the early 1988s, during a period when large redshift mapping projects were transforming astronomy from flat star charts into true three-dimensional maps of the universe. An early famous description characterized the Boötes Void as roughly 1 million cubic megaparsecs of space containing very few galaxies, which is a way of saying the emptiness is not small and local, but spread across an enormous cosmic volume. Follow-up work in the 1980s confirmed that a very large void-like region was present by collecting more redshift measurements, showing that the missing galaxy pattern wasn't a fluke of a single survey bar. One survey report describes the void with a radius of about 62 megaparsecs, a distance unit astronomers use because it's convenient for describing structures far beyond the Milky Way. A radius of about 62 megaparsecs corresponds to roughly 200 million light-years, which means that if you could travel at the speed of light, it would still take about 200 million years just to go from the center to the edge. A commonly cited diameter for the Boötes Void is around 330 million light-years across, emphasizing that this is a feature on the scale of the largest structures that early redshift surveys could meaningfully map. Some of the earliest evidence came from pencil beam redshift surveys, which are narrow, deep observations that sample a thin line of the universe far into space, like taking a core sample through layers of cosmic structure. In one educational summary, the initial claim involved 3 pencil beam surveys, separated by about 35 degrees on the sky, so the missing galaxy pattern wasn't limited to a single narrow direction. That same summary notes a notable gap around velocities near 15-000 kilometers per second along those directions, which is a redshift-based way of describing a distance range where galaxies were unexpectedly absent. Redshift gaps are interpreted as distance ranges with fewer galaxies than expected if galaxies were spread out evenly, which is why a gap becomes meaningful evidence for a true underdense region. The same summary describes a follow-up sample of about 240 bright galaxies to test the gap, because checking a larger, carefully defined sample helps confirm whether the emptiness is real or just a Bell sampling artifact. That follow-up is described as finding none in a particular velocity window, which strongly supported the idea that something genuinely unusual was happening in that slice of cosmic distance. The summary also contrasts the observed count with an expected count under a uniform distribution, which is essentially a statistical reality check, if you expect many galaxies but see nearly none. Simplest explanation is a true underdensity. In these surveys, redshift is used as a proxy for distance because the universe is expanding, so distant galaxies tend to have their light stretched to longer, redder wavelengths as space itself expands along the line of Fermat. Sight. Put simply, a larger redshift usually indicates a more distant galaxy in the smooth Hubble flow, even though local gravitational motions can add small deviations on top of that overall expansion. Trend. The label void refers to galaxy scarcity rather than a complete absence of matter, because even the emptiest large regions still contain dark matter, thin gas, radiation, and at least a few galaxies. The Boötes Void sits within the broader cosmic web, the large-scale pattern where galaxies gather in filaments and walls, leaving big, quieter spaces in between. Cosmic voids are common features between filaments rather than singular anomalies, so the Boötes Void is dramatic in size, but it belongs to a general family of structures produced by the universe's growth, over time. The Boötes Void is often called a supervoid because it's on the large end of known void sizes, making it a memorable example of just how strongly the universe can separate into crowded regions and sparse ones. In some descriptions, the near edge of the Boötes Void is associated with the Hercules superclusters, reminding us that emptier regions are often bordered by richer, denser concentrations of galaxies. Cataloging a void depends on the depth of a survey, its angular coverage across the sky, and its selection function, meaning the practical details of what the survey can and cannot detect shape the final map. Void boundaries are often defined statistically by how galaxy density changes with distance from a chosen center, so the edge is usually where the galaxy counts rise back toward more typical levels. Later, searchers filled in some of the void by adding more galaxies once fainter objects and different galaxy types were included, showing how deeper data can reveal structure that bright galaxy surveys miss. Some studies used infrared-selected galaxies, including ERAS-related samples, to probe dusty, star-forming systems, because infrared light can slip through dust that may hide a galaxy's brightest features. Invisible light surveys. Infrared surveys can detect galaxies that are not prominent in optical catalogs, especially if dust absorbs visible light and re-emits it in infrared, or if a galaxy's stars are spread out in a low surface, brightness way. One long effort, analyzing IRA's data, identified dozens of galaxies within the Boötes Void boundaries, illustrating that the region is underdense, but not perfectly empty when you look with broader and deeper tools. Many galaxies known in the Boötes Void were found via objective prism surveys that emphasize emission lines, a technique that helps reveal galaxies where glowing gas clouds shine strongly at specific wavelengths. Emission line selection tends to favor star-forming galaxies with strong nebular lines, because intense regions of young stars energize surrounding gas, making it glow in characteristic spectral features. Some late 1980s spectroscopic follow-up work is described as discovering 2 more galaxies in the void, which is a small number, but important because each confirmed member helps map how the void is populated. That same line of work estimated the density of emission line galaxies in the void as lower than in typical field environments, suggesting that even galaxy types that are easy to catch via emission can still be rarer in cherry. Deep underdensities. The Case Low Dispersion Northern Sky Survey served as one source of candidate galaxies toward the Boötes region, demonstrating how multiple sky surveys can be combined to hunt for faint or unusual objects. Some studies emphasize that void galaxies are not necessarily exotic, but often ordinary galaxies living in low-density surroundings, meaning the environment is unusual even if the galaxies themselves can look familiar. Spectroscopy is essential for confirming whether a candidate galaxy truly lies within the void's distance range, because only a measured redshift can reliably place it in three-dimensional space. A later study examined the physical properties of a sample of a few dozen Boötes Void galaxies using emission line diagnostics, which can reveal how actively they form stars and what kind of energetic processes dominate their light. In that sample, many galaxies were classified as H2 type systems, meaning their emission lines look like those produced by star-forming regions powered by young, massive stars, rather than by a dominant active nucleus. That same work identified a small number of extreme starburst galaxies within the void sample, showing that intense bursts of star formation can happen even in places where galaxies are widely spaced. A key observational theme is that very low-density environments can still host active star formation, meaning a galaxy doesn't need to live in a crowded cluster to keep building new stars. Void galaxies are often late-type and gas-rich compared with many cluster galaxies, which fits the idea that, without harsh environmental stripping, they can retain the cold gas that fuels ongoing star formation. The intergalactic medium in a void is generally expected to be less dense than average, and that can influence how gas is accreted over time, how easily galaxies find new fuel, and how their surroundings respond to it. Outflows. Because close neighbors are fewer, strong tidal interactions and major mergers are typically less frequent inside void interiors, which changes the typical life story of galaxies compared with those in dense groups and clusters. When galaxies have fewer close encounters, it can quietly reshape how they grow over billions of years, because major interactions are one of the main ways galaxies stir up their gas, build central bulges, and trigger intense bursts of star formation. In a void, where strong gravitational tugs from neighbors are less common, galaxies may evolve in a slower, steadier way, with fewer dramatic, merger-driven changes compared with galaxies living in crowded regions. Even inside a void, truly perfect isolation is rare, because some galaxies still have nearby companions, small groups, or loose associations. So rather than thinking of a void galaxy as completely alone, it's more accurate to picture a wide spectrum of environments, ranging from nearly solitary systems to pairs and small families that just happen to exist within a much larger, underdense region. Neutral hydrogen surveys are especially valuable in voids because some galaxies can be rich in cold gas yet faint in starlight, particularly low-mass dwarfs or low-surface brightness systems. By looking for the 21-centimeter emission from hydrogen, radio telescopes can reveal galaxies that optical surveys might miss, giving a more complete picture of what actually lives inside a cosmic void. A dedicated H1 survey program targeted known Boötes Void galaxies using 21-centimeter observations, focusing on the cold hydrogen that often serves as the raw fuel for future star formation. This kind of targeted campaign helps researchers measure how gas-rich void galaxies are, how their gas is distributed, and whether their environments differ in a measurable way from galaxies in denser parts of the cosmic web. H1 observations can also uncover very faint companions through their gas emission, even when those companions are hard to see in visible light. That matters because a small, gas-rich neighbor can still influence a galaxy over time through weak interactions, shared gas flows, or subtle gravitational effects, showing that even in emptier space, galaxies can have meaningful relationships. Some Boötes Void galaxy candidates were identified using ERA's point source and faint source catalogs, along with optical searches, because different kinds of galaxies stand out more clearly at different, quote, wavelengths. By combining infrared and optical selection, astronomers increase the chance of finding dusty or actively star-forming galaxies that would otherwise blend into the background or appear too faint in standard optical catalogues. In redshift space discussions, the void is sometimes described using a characteristic velocity span rather than a physical length, because redshift surveys naturally measure how fast galaxies appear to be receding. This approach is practical. Instead of drawing a perfect geometric boundary in space, researchers can describe AEDE range of redshifts, where galaxies are unusually scarce, which corresponds to a wide distance interval. A velocity span of several thousand kilometers per second translates to a very large distance range when interpreted through the Hubble expansion. In everyday terms, that means the underdense region isn't just a small patch with a few missing galaxite covers, an enormous stretch of space along the line of sight, wide enough to contain countless galaxy groups if it were filled at average cosmic density. The Boötes Void became historically notable because it was among the first very large voids widely discussed in modern redshift survey astronomy, at a time when these 3D maps were still new and surprising. Its scale helped convince many astronomers that the universe's large-scale structure is strongly patterned, with prominent walls and filaments surrounding large, quieter regions. That discovery helped cement the void-and wall picture of the universe, where galaxies are not sprinkled evenly, but instead form an interconnected network. In this view, dense regions act like the bright threads of a web, while voids form the spacious cells between them, making the overall structure look more like a cosmic foam than a uniform fog of galaxies. The cosmic web framework explains voids as natural outcomes of gravitational growth from tiny initial density fluctuations, because even a small imbalance in matter density early on can grow over time. Where matter started slightly denser, gravity pulled more material in. Where it started slightly less dense, matter drifted away, gradually carving out expanding underdense regions. Regions that begin slightly underdense tend to expand faster than average, because there is less gravity pulling inward to slow them down. As the universe expands overall, these underdense patches effectively empty out relative to their surroundings, with matter streaming outward toward neighboring overdense filaments and clusters. This outward flow makes voids emptier over time in many simulations and analytic models, which means a void is not just a static gap, it is an evolving feature. Over billions of years, void interiors can become more rarefied, while their edges can become more sharply defined as matter accumulates in surrounding walls. Void growth is often described as hierarchical, meaning smaller voids can merge into larger ones as the separating walls thin, shift, or are rearranged by cosmic evolution. The result is that today's largest voids may be the products of many smaller underdense regions gradually combining into bigger, more coherent expanses. A common hypothesis in popular explanations is that the Boötes Void could reflect the coalescence of smaller voids, which is one intuitive way to picture how something so large might form. While the detailed history depends on the surrounding structure and the specific definition used, the merging bubbles idea matches the broader concept of hierarchical void evolution in large-scale structure. Even large voids do not contradict standard lambda-dumb cosmology in mainstream treatments, because the model naturally produces both dense knots and deep underdensities as structure grows. In that framework, the Boötes Void is dramatic, but it is not a sign that the basic physics of cosmic evolution has failed. It is a strong example of the kind of variety large-scale structure can create. The number of galaxies you expect inside a void depends strongly on the magnitude limit of the survey and the assumed average density, because what counts as a galaxy in your data changes with depth. If a survey only includes very bright galaxies, A void can look extremely empty if it includes fainter systems. The same region can contain many more detected members. A region can appear emptier in bright galaxy samples while still containing numerous faint dwarf galaxies below the detection threshold. And this is a key reason void studies often stress survey completeness. Many dwarfs are dim, small, and diffuse, and over great distances they can be difficult to find. So deeper observations can gradually reveal a richer, though still underdense, population. Voids are typically defined relative to a mean density, rather than as perfectly empty volumes, meaning void is a statistical word. It tells you that, compared to an average region of the universe at the same scale, the density of galaxies and often the underlying matter is significantly lower, even if it is never literally zero. Some definitions use a density contrast threshold to classify deep void interiors, which is a more precise way to quantify emptiness. Instead of relying on a vague sense of few galaxies, researchers can set a mathematical cutoff, like being below a certain fraction of the mean density, to distinguish the emptiest cores from the less empty outskirts. Different void-finding algorithms can identify slightly different boundaries in the same dataset, because there is no single perfect way to draw the edge of something that fades gradually. One method might emphasize the lowest density center, another might emphasize the surrounding ridge of galaxies, and a third might group neighboring low-density zones into one larger structure. Void finders can use geometric approaches like watershed methods, density field reconstructions, or dynamical information, and each choice highlights different aspects of the cosmic web. Watershed methods, for example, treat the density field like a landscape and identify basins of low density, while dynamical methods try to connect voids to the flow of matter through gravity. Redshift distortions from peculiar velocities can stretch or compress voids along the line of sight in redshift space, creating a subtle mapping challenge. Because galaxies don't only follow the Hubble expansion, some also drift due to local gravitational pulls. Their redshifts can include extra motion that slightly shifts their apparent positions in 3D maps. Survey masks and incomplete sky coverage can bias void identification, especially for very large voids, because missing data can mimic emptiness. If a region of the sky has fewer measured redshifts due to observational limits, it can look like a void even when galaxies are present, so careful corrections are needed to separate real cosmic structure from gaps in D. Coverage. Large redshift surveys, such as SDSS, enabled systematic void catalogues beyond early thin slice surveys, because they mapped huge numbers of galaxies over wide areas. With dense sampling and consistent selection, modern surveys can identify many voids in a uniform way, allowing researchers to compare void properties statistically rather than relying on a single famous example. Modern void science often focuses less on one named void and more on ensembles of voids, because large samples reveal patterns more reliably. By analyzing many voids together of different sizes and in different regions, scientists can measure typical density profiles, shapes, and galaxy properties with much better confidence. In many simulations, void interiors are dominated by dark matter and diffuse gas rather than luminous galaxies, which means the emptiness is mainly about light, not about absolute content. Galaxies trace the peaks of the matter distribution. So when galaxy density is low, it usually indicates a broader reduction in matter density, even though dark matter and gas still fill the region. The total mass within a void volume can still be enormous simply because the volume is so large. Even if the density is well below average, a sphere hundreds of millions of light years across contains so much space that the remaining dark matter and gas add up to a vast amount of mass in absolute terms. Dark matter in voids tends to form low-amplitude filaments and small halos rather than rich clusters, reflecting the calmer gravitational environment. Instead of massive, tightly bound concentrations, you find smaller structures, fewer large halos, more modest ones often arranged in faint threads that are harder to detect because they host fewer bright glow. Galaxies. Voids can be used as cosmological probes because their shapes and dynamics respond to the universe's expansion history. As the expansion rate changes over time, it subtly affects how quickly voids grow, how matter flows around them, and how their density profiles evolve, making void statistics a potential tool for testing. Cosmological models. Some recent work emphasizes that void properties can constrain cosmological parameters in principle, because different cosmologies predict different patterns of void growth and distribution. By comparing observed void catalogs to simulated universes with varying parameters, researchers can look for the versions that best reproduce the real cosmic web. Void stacking analyses average many voids together to reduce noise and reveal subtle signals, like weak gravitational lensing. A single void is usually too lightweight to bend background light strongly on its own, but when many voids are aligned and averaged, their collective statistical effect can become detectable. Gravitational lensing by voids is weaker than lensing by clusters, but it can still be measured statistically, often as a slight change in the shapes or apparent sizes of background galaxies. This weak lensing provides a direct way to probe the matter distribution, including dark matter in and around voids, not just the distribution of visible galaxies. Voids can contribute to integrated Sachs-Wolf type effects in some analyses, where large-scale structures correlate with subtle temperature patterns in the cosmic microwave background. In simple terms, photons traveling through evolving gravitational potentials can gain or lose tiny amounts of energy, and voids, as underdense regions, can play a role in that subtle imprint when conditions are right. Baryon acoustic oscillations leave an imprint on the large-scale distribution of matter, and void statistics can reflect that imprint too. BAO is like a faint, ancient ripple pattern from the early universe, and because it influences how matter is arranged on very large scales, it can affect both white clusters form and how voids are spaced. Some studies treat void centers as special points for measuring large-scale isotropy and homogeneity, because voids sample the underdense side of the cosmic web. By looking at many voids across the sky, researchers can test whether the universe looks statistically similar in different directions and whether the overall large-scale patterns match expectations. The Boötes Void is distant enough that its look-back time is significant, though it is not an extreme early universe object like the first galaxies. That means when we observe galaxies around its distance range, we see them as they were hundreds of millions of years ago, giving a slightly earlier snapshot of cosmic structure. At hundreds of millions of light years, galaxies are observed as they were hundreds of millions of years in the past, because light takes time to travel. This isn't just a poetic idea, it's a practical part of astronomy. Every deep survey is also a history book, showing different eras of the universe depending on distance. The void's distance from Earth is often given for its center, but the near and far sides cover a wide range, because the structure has thickness along our line of sight. So when people quote a single distance, it's best understood as a convenient reference point, not a strict boundary where the void begins and ends. Because the void is defined by galaxy scarcity, its center can shift depending on the sample used, such as whether you count only bright galaxies or include faint dwarfs. With different tracers and different thresholds, the lowest density point may move slightly, reflecting the fact that the void's interior is a region, not a single pinpoint. Boötes Void refers to a direction on the sky, while the physical void is a three-dimensional structure in space. In other words, the name tells you where to look from Perth, but the thing itself is a large volume at great distance, not a feature painted onto the stars of the constellation. The constellation label does not mean the void is inside the Milky Way, because constellations are patterns on our sky, not physical groupings at one distance. The Boötes Void lies far beyond our galaxy and even beyond the nearby galaxy groups, in the much larger scale realm where cosmologists map the structure of the universe. The scale of the void is vastly larger than any single galaxy, and far larger than typical galaxy groups, which helps put it in perspective. A galaxy might be 100,000 light-years across, and a galaxy group might span a few million light-years, but a void like Boötes stretches across hundreds of millions of light-years. Its scale is comparable to the largest structures mapped in early redshift surveys, which is part of why it made such an impact. It was a clear sign that cosmic structure exists on astonishingly large scales. Seeing a feature that big pushed astronomers to think in terms of walls, filaments, and immense empty regions rather than small local clusters alone. Large voids like this help demonstrate that the universe is not uniformly filled with galaxies even on very large scales, at least not in the everyday sense of evenly sprinkled. Instead, galaxies cluster strongly, leaving large spaces where the density drops dramatically, yet still in a way that fits into the overall statistical patterns predicted by modern cosmology. The phrase, "great nothing," is a casual nickname sometimes used for the Boötes Void, and it's meant to highlight how dramatic the scarcity of galaxies can seem when you first learn about it. Scientifically, though, it's not an official category or a special type of object, just a memorable way to communicate that, compared with surrounding regions, this part of space contains far fewer visible galaxies than we might intuitively expect. Some eras-based analyses reported only a few eras, galaxies inside the void for certain definitions and samples, which is a reminder that different selection methods can paint different pictures. IRAS, an infrared survey, tends to highlight galaxies with warm dust and active star formation, so if only a few show up in that catalogue within the void, it suggests that this particular infrared bright population is especially sparse there, or that the survey's sensitivity and selection limits simply miss many fainter systems. When some studies find a few galaxies and others find dozens, the difference often comes down to magnitude limits and boundary choices rather than disagreement about whether the void exists. If you only count brighter galaxies, the interior can look almost empty. But once you include dimmer galaxies and broaden the definition of the void's edges, the same region may contain many more detected members, while still being underdense overall. Objective prism surveys can detect compact emission line galaxies that might be underrepresented in bright optical catalogues, because the technique is designed to flag strong spectral features rather than relying solely on how bright a galaxy looks in broadband light. This matters in voids because some galaxies may be small, faint or low in surface brightness, yet still have intense pockets of star formation that produce bright emission lines. H1 surveys are able to detect galaxies with high gas-to-starlight ratios, including low surface brightness galaxies that blend into the background in visible images. The 21-centimeter signal comes from neutral hydrogen, and it doesn't care whether a galaxy looks pretty in optical light, so it can reveal objects that are otherwise nearly invisible except as faint 18. Smudges. Some studies look closely at whether star formation in Boötes Void galaxies is normal for their mass or unusually elevated, because environment might influence how galaxies get fuel and how often star formation is triggered. By comparing star formation rates to galaxy mass, researchers can see whether void galaxies are quietly forming stars at expected levels, or whether they show signs of unusual bursts relative to their size. Spectral line ratios are a key tool for distinguishing H2 region-like excitation from AGN-like excitation, especially in galaxy centers. In plain language, by comparing the strengths of specific emission lines, astronomers can infer whether a galaxy's glow is mostly powered by young stars heating nearby gas, or by a more concentrated, energetic process like material falling into a supermassive black hole. Extreme starbursts in void samples show that very high star formation can still happen without a dense cluster environment nearby. This is important because it challenges the simple idea that galaxies need frequent collisions or strong external pressure to light up with intense star formation. Instead, internal instabilities, smaller interactions, or fresh gas inflow can also ignite powerful bursts. Gas accretion from the intergalactic medium is one mechanism that can sustain star formation without frequent mergers, because galaxies can slowly draw in fresh material from their surroundings. Even in a void, there is still diffuse gas thin, mostly invisible, but real-earned over long timescales. Gentle inflow can replenish a galaxy's star-forming reservoir. Small-scale interactions can still occur inside voids, because galaxies can form pairs or triplets even within a larger underdense region. These interactions may not be as frequent as in dense filaments, but when they happen, they can still disturb gas, trigger star formation, and create subtle changes in shape and motion, showing that void does not ATS mean no dynamics. Void galaxies offer a natural laboratory for separating nature from nurture in galaxy evolution, meaning researchers can ask what a galaxy does mostly because of its own mass, gas content, and internal physics, versus what it does because neighbors and environment push and pull on it. In a sparse region, many of the strongest external influences are reduced, so internal processes can be studied with fewer confounding effects. In hierarchical structure formation, underdense regions expand and matter gradually evacuates toward denser nodes in the cosmic web, like water flowing off a gentle hill into valleys. Over cosmic time, gravity amplifies the differences between slightly dense and slightly sparse regions, so voids become emptier as filaments and clusters become richer. The interior of a mature void can have a density contrast far below the cosmic mean, depending on how the void is defined and measured. This density contraster is a precise way of saying how much less stuff is here than average. And in deep void cores, that difference can be dramatic, even though it is never truly zero. Void edges often coincide with sheets or walls of galaxies where density rises sharply, because evacuated matter doesn't disappear, it relocates. As material drifts outward from void interiors, it tends to collect in the surrounding structures, creating boundaries that look like walls or shells of galaxies when viewed in three-dimensional maps. Those galaxy walls appear clearly in wedge diagrams from redshift surveys, where distance is plotted outward and angle is plotted sideways, creating a slice-like view of the universe. In these diagrams, dense regions show up as bright arcs and clusters of points, while voids show up as wide gaps, visual evidence of the cosmic web. Early redshift surveys were smaller and shallower than today's surveys, which made the identification of very large voids more surprising at the time. With fewer data points, astronomers had to be careful about statistical flukes, but when a gap remained across multiple survey lines and follow-ups, it became a strong clue that a huge, underdense region was real. Modern surveys reduce cosmic variance by sampling much larger volumes and more directions across the sky, which means the maps are less dependent on chance. Cosmic variance is essentially the idea that one patch of the universe might look unusually dense or unusually empty just by luck. Bigger surveys average over more space, making the overall conclusions more stable. A major methodological challenge is telling the difference between a true underdensity and an observational selection effect, because missing data can imitate emptiness. If a survey struggles to measure redshifts in a particular direction or misses faint galaxies, that region can look artificially sparse. So careful corrections and multiple methods are important. Selection effects can come from dust extinction in the Milky Way, incomplete spectroscopy, or magnitude limits that cut off faint galaxies. For example, dust in our own galaxy can obscure background galaxies, and if redshift measurements are incomplete in a region, the resulting map might show a gap that reflects missing observations rather than real bar. Cosmic structure. Another challenge is that redshift surveys measure distances with uncertainties due to peculiar velocities, meaning galaxies don't only follow the smooth expansion of the universe. Local gravitational pulls can add extra motion toward or away from us, slightly shifting a galaxy's redshift and making it appear a bit closer or farther in a redshift-based distance map than it truly is. Even with these complications, the Boötes Void remained a landmark example in discussions of the cosmic web, because its scale and the repeated confirmation across methods made it hard to dismiss. It became a reference point, something astronomers could point to when explaining how large-scale structure includes not only dense clusters, but also enormous underdense regions. The volume of the Boötes Void depends on whether you model it as a sphere, an ellipsoid, or a more irregular shape, because the real structure doesn't have a perfectly sharp boundary. Different choices are like drawing slightly different outlines around a cloud. The overall picture remains, but the exact measured volume can shift. Modeling voids as spheres is often a simplification used for communication and for some calculations, because spheres are easy to describe mathematically. Even if a void is somewhat stretched or lopsided, a spherical approximation can still give a useful sense of its characteristic size, as long as we remember it's an idealization. In simulations, real void boundaries are often complex and shaped by surrounding filaments and walls, like the uneven edges of bubbles packed together. This complexity matters because it means voids are not isolated objects. They are defined by the surrounding cosmic web, and their shapes reflect how matter has flowed and accumulated over time. Some explanations suggest galaxy distribution inside the Boötes Void is not uniform and may include internal substructure, meaning the few galaxies that exist there may not be spread evenly. Instead, they might trace faint internal filaments or small groupings, showing that even empty regions can have subtle patterns. The idea of a cylindrical region through the void's center appears in some secondary summaries, which is one way to describe a possible internal arrangement of galaxies along a preferred direction. It's not the same as saying the void is truly a cylinder. Rather, it suggests that within the larger underdensity, there could be a thread-like feature or corridor where galaxies are slightly more common. Internal substructure can include tenuous filaments of faint galaxies connecting to surrounding walls, which fits what simulations often predict. The cosmic web doesn't abruptly stop at a void boundary. Instead, it can thin into very faint strands that cross the void, carrying a small population of galaxies and dark matter halos. In underdense simulations, small dark matter halos can still form inside voids, even though massive cluster-scale halos are rare there. A dark matter halo is the invisible gravitational Homer where a galaxy can form, and while the void environment suppresses the formation of very large halos, it doesn't prevent smaller halos from existing. The mass function of halos in voids is shifted toward lower masses compared with average density regions, meaning you expect fewer big halos and more small ones, relative to the cosmic mean. This is a straightforward consequence of having less matter available locally. It is harder to build something massive when the surrounding material is sparse. That shift influences the typical luminosities and morphologies of void galaxies, because halo mass affects how much gas can be captured, how strongly it can be held against feedback, and how efficiently it can form. Stars. Lower mass halos often host smaller, fainter galaxies, frequently with more irregular shapes and a stronger sensitivity to gas flows and stellar winds. Because voids contain fewer bright galaxies, many early void catalogues focused on bright galaxy voids rather than on dwarf-rich interiors, largely due to observational limitations. Bright galaxies were easier to measure and map at large distances, So early studies naturally defined voids by the absence of those bright tracers, even though many faint galaxies could remain undetected. A void's expansion can create coherent outflow velocities of matter away from its center, meaning that, on average, material tends to drift outward rather than inward. This is not like an explosive wind, but more like a slow, large-scale streaming motion driven by gravity. Because the center is underdense, there is less gravitational pull holding matter in place, so the surrounding universe effectively pulls matter outward toward denser regions. Those outflows contribute to peculiar velocities observed in galaxies near void boundaries, which are velocities on top of the smooth Hubble expansion. When astronomers measure a galaxy's redshift, they see the combined effect of cosmic expansion plus local gravitational motions. Near void edges, the outward drift away from the void can slightly change the redshift, subtly affecting distance estimates and the apparent shape of the void in redshift maps. Voids are sometimes described as basins in the gravitational potential landscape, in contrast to overdense regions that act more like deep gravitational wells. In this picture, the universe is like a gentle terrain. Clusters are valleys where matter gathers, and voids are higher, flatter regions where matter has drained away, creating a different kind of gravitational environment that shapes how galaxies and gas move. Dynamical void finders try to reconstruct voids using velocity fields or gravitational potential information, not just simple galaxy counts. Instead of only asking, where are there few galaxies? These methods also ask, where is matter flowing outward in a coherent way? Using that dynamical behavior as a clue to identify underdense regions and to estimate their true physical structure. Some void research treats voids as sensitive probes of dark energy because the cosmic expansion history influences how voids grow and empty out. Dark energy affects the rate at which the universe expands, and that expansion rate changes the balance between gravity pulling matter together and expansion stretching space apart. So, the size distribution and evolution of voids can carry information about the underlying cosmology. In some analyses, modified gravity models predict different void profiles compared with standard gravity, making voids a testing ground for alternative theories. Because voids are relatively low-density environments, they can be places where certain modified gravity effects might be less screened and therefore easier to detect, at least in principle, through careful statistical comparisons of void shapes, density profiles, and galaxy motions. Voids are generally less affected by nonlinear baryonic feedback than the dense cores of clusters, which can simplify some interpretations. In dense regions, processes like strong cooling, energetic outflows, and complicated gas physics can significantly reshape matter distributions. But in voids where everything is thinner, some of those effects can be reduced, making it easier to connect observations to underlying gravitational structure. Even so, galaxy formation physics still matters inside void halos, especially for dwarf galaxies, because small systems are very sensitive to how gas heats, cools, and escapes. A dwarf galaxy in a low-mass halo can lose gas more easily through stellar winds and supernova feedback, and it can struggle to pull new gas in. So even in a simple environment, the internal physics remains crucial. Environmental quenching processes common in clusters such as RAM pressure stripping are weaker in void interiors because the surrounding gas is thinner and galaxy speeds relative to that gas can be lower. In clusters, galaxies plow through hot intracluster gas like a wind tunnel, which can sweep away their cold gas and shut down star formation in a void. That stripping mechanism is much less intense, allowing many galaxies to keep their fuel. As a result, void galaxies can remain gas-rich and star-forming for longer on average than similar mass galaxies in dense clusters, because they experience fewer harsh external processes. This doesn't mean every void galaxy forms stars rapidly, but it does mean the overall population may retain more cold gas and show more ongoing star formation than galaxies subjected to the strong Bray environmental pressures of cluster life. The Boötes Void is sometimes compared with other named voids, but whether it is largest depends on definitions, datasets, and what counts as a void versus a broader underdensity. Different surveys map different volumes and use different criteria, so comparisons often require careful translation between methods rather than simple ranking. Some compilations list very large underdensities, such as the KBC underdensity and the local void as distinct from Boötes, highlighting that emptier than average regions can appear at multiple scales. And distances. These names often refer to different contexts. Some are local cosmic neighborhood features, while others are deep sky underdensities, so the comparison is more about illustrating variety than identifying a pebble. Single champion. Many void labels in popular lists mix deep voids with broad underdensities, which can be confusing because those are not always the same thing. A deep void is a sharply underdense region with a clear boundary in galaxy maps, while a broad underdensity may be a gentler dip in density over a larger area, sometimes described as a local hole or underdense region rather than a classic void bubble. The Boötes Void is often cited as a deep, prominent void discovered in early survey work rather than as a modern catalogue object, because its fame comes from the role it played in the history of redshift mapping. Modern void catalogues may label many voids systematically without giving each a memorable name, but Boötes remains a classic example discussed in teaching and popular explanations. Supervoid is not a formal IAU category. It's an informal term used in literature and popular science to describe an especially large void. It's similar to how people might say supercluster in a descriptive way useful for communication, but not necessarily a strict classification with one universally agreed boundary. Voids occupy a large fraction of the universe's volume, even though most galaxies reside outside void interiors, because emptier regions take up more space. If you imagine the cosmic web as foam, most of the volume is in the bubble interiors, while most of the material is concentrated in the bubble walls and junctions. This volume-filling nature means that, geometrically, empty space dominates the cosmic web, even though it doesn't dominate the light we see. When astronomers map the universe, the bright points are galaxies, but the spaces between them are immense, and voids represent the most extreme examples of that spaciousness. Filaments and walls occupy less volume but contain most luminous matter, which is why the universe looks clumpy in galaxy maps. Matter has flowed into these structures over time, making them rich in galaxies, while the interiors of voids were depleted as that matter migrated outward. Voids can be thought of as the negative space of large-scale structure, meaning they define the cosmic web by their absence as much as by any positive structure. In practice, identifying voids helps identify the surrounding walls and filaments too, because the boundary of a void is often where the galaxy density rises into those brighter features. In three-dimensional maps, voids often appear as contiguous bubble-like regions separated by sheet-like galaxy walls, creating a pattern sometimes compared to a honeycomb or foam. This appearance is not just a visual metaphor. It reflects how gravity and expansion together can produce a network of dense sheets surrounding large, underdense volumes. The original Boötes Void paper emphasized how rare it would be to find so few galaxies in such a large sampled volume if galaxies were uniformly distributed. That statistical framing was crucial. Rather than relying only on an impressionistic, "it looks empty," the work argued that the emptiness was far beyond what random fluctuations would typically produce. As surveys grew in size and quality, large voids became expected features rather than shocking anomalies, because the cosmic web became clearer and more comprehensively mapped. Once astronomers had enough data to see multiple examples, it became evident that voids are a fundamental part of how matter organizes itself on large scales. Boötes remains historically important because it helped motivate broader mapping programs, encouraging astronomers to measure more galaxy redshifts and chart the universe more thoroughly. Discoveries like this acted as signposts that the universe's structure was richer and more patterned than previously confirmed by smaller datasets. The practice of using redshift surveys to create three-dimensional maps became central to observational cosmology, partly because findings like the Boötes Void demonstrated how much information was hidden in the third dimension of distance. Once distance was added to sky position, the universe transformed from a scattered set of dots into a structured network. The Boötes Void is not a true vacuum region because it contains background radiation, dark matter, diffuse gas, and at least some galaxies. Even in its emptiest parts, space is filled with fields, particles, and low-density material. What changes is the concentration of large, luminous structures, like bright galaxies and clusters. Intergalactic gas in voids can be ionized and extremely diffuse, making it difficult to observe directly in emission because the glow from such thin material is very faint. Much of the gas between galaxies is so spread out that it doesn't shine brightly, so astronomers often detect it indirectly rather than seeing it as a clear glowing cloud. Absorption line spectroscopy against background quasars is one method for detecting diffuse gas, because the gas can leave subtle fingerprints in the light from a bright background source. If a quasar's light passes through thin intergalactic material, certain wavelengths can be absorbed, revealing the presence and properties of that otherwise invisible gas along that particular line of sight. Voids are expected to host fewer massive galaxy clusters, so X-ray bright cluster emission is rarer inside them, since clusters are among the strongest X-ray sources in the large-scale universe. Cluster gas is hot and dense enough to emit X-rays strongly, but void interiors are less likely to contain the massive gravitational wells that gather and heat such gas to X-ray temperatures. Some studies have searched for X-ray emitting sources associated with void galaxies using all sky X-ray survey data, looking for signs of active nuclei, X-ray binaries, or hot gas. Even if voids lack rich clusters, individual galaxies can still produce X-rays through processes tied to black holes or energetic stellar remnants, so these searches help characterize what kinds of energetic systems exist in low-density space. Galaxy surveys toward Boötes have used multi-wavelength approaches, optical, infrared, and radio because different bands pick up different galaxy populations. By combining these tools, researchers can better avoid bias and can build a more complete census of what's actually present, from dusty star formers to gas-rich dwarfs and faint optical systems. The Hubble constant provides the basic conversion between recession velocity and distance in the nearby to intermediate universe, which is why it shows up naturally when people describe voids using redshift and at-al. Velocity. In simple terms, if you know how fast a galaxy appears to be receding because of cosmic expansion, the Hubble constant lets you estimate how far away it is, and that helps map where emptier regions begin and end along a line of sight. Because cosmological parameters have been refined over decades, older void size estimates are sometimes written in h-scaled units, where distances are expressed relative to a normalized Hubble constant. This is a bookkeeping system. It allows results to stay usable, even if the best estimate of the Hubble constant changes, because you can rescale the numbers to match the modern value, rather than rewriting the entire analysis. The megaparsec, abbreviated MPC, is the standard unit for large-scale structure studies, including void radii, because it's a convenient step size for cosmic distances. 1 megaparsec is about 26 million light-years, so when astronomers say a void is tens of megaparsecs across, they're talking about distances so large that light would take hundreds of millions years to cross them. 1 million cubic megaparsecs is an immense volume compared with typical galaxy cluster volumes, which helps explain why the Boötes Void drew attention. Even if the density is only modestly below average, the sheer size of that volume means the missing matter, and galaxies represent an enormous amount of structure on the grandest scales that were being explored when the void was first discussed. In some survey descriptions, the Boötes Void's redshift space center is reported around a recession velocity near 500 kilometers per second, providing a practical reference point for where the underdensity is most pronounced. This kind of value is useful in observational work because it lets researchers define a distance range to target for deeper searches, follow-up spectroscopy, or multi-wavelength observations. A velocity-centered definition highlights that void membership is often defined by redshift intervals rather than by a perfectly clean geometric boundary. That's because redshift surveys naturally give you a distance axis in terms of velocity, so it's often simpler to say galaxies are scarce between these velocities than to claim the void has a crisp physical edge like a solid sphere. Some galaxies that appear projected in front of the void on the sky are not actually void members because they lie at different distances along the same line of sight. This is a key idea in 3D mapping. The sky can place objects near each other in angle, but only distance measurements reveal whether they are truly neighbors in space or merely aligned from our viewpoint. Conversely, a faint void galaxy can be overlooked in imaging if it has low surface brightness, meaning its light is spread out so thinly that it blends into the background. These galaxies can be physically real and gas riche, but visually subtle, and at large distances they become especially challenging to detect without deep, careful observations. Survey completeness tends to drop for low surface brightness galaxies, which can bias galaxy counts and make a void appear emptier than it truly is. If your survey systematically misses a particular galaxy population, then the absence of those galaxies in the catalogue isn't proof they aren't there. It might simply reflect the limits of the observing strategy, the instruments, or the data processing thresholds. This is one reason radio H1 surveys are such valuable complements to optical surveys in void environments, because neutral hydrogen can reveal galaxies regardless of how faint their starlight appears. A gas-rich dwarf may be hard to see optically, but relatively clear in 21 centimeter emission, allowing astronomers to recover part of the population that optical catalogues tend to undercount. Some studies of Boötes Void galaxies emphasize H-alpha and other emission line measurements to estimate star formation activity, because these lines trace regions where hot young stars are energizing surrounding hydrogen gas. When a galaxy forms massive new stars, those stars emit strong ultraviolet radiation that causes nearby gas to glow, and that glow becomes a direct sign of ongoing star formation. Emission line equivalent widths provide a relative measure of ongoing star formation compared with older starlight, because they compare line strength to the underlying continuum. A larger equivalent width often indicates that recent star formation is strong compared with the older stellar population, which helps researchers assess whether a galaxy is actively growing today or forming tail stars more quietly. Metallicity diagnostics can be derived from strong line ratios to estimate chemical enrichment, offering insight into how a void environment may shape a galaxy's history. Metallicity in astronomy refers to elements heavier than helium, which are made inside stars and spread through gas by winds and supernova. So measuring metallicity helps reveal how much past star formation and recycling has occurred. Low-density environments can correlate with slower enrichment histories for some low-mass galaxies, though results vary by sample and method. One intuitive reason is that if galaxies form stars more slowly or have fewer interactions that trigger bursts, they may build heavy elements more gradually, and their gas can remain comparatively less enriched for longer. Some void galaxy samples show a high fraction of late-type morphologies, meaning disk-like, spiral, or irregular galaxies that often still contain cold gas and ongoing star formation. This contrasts with dense cluster environments, where many galaxies become gas pur and more spheroidal over time, partly due to environmental stripping and repeated interactions. With fewer close encounters, disk galaxies in voids may experience fewer strong perturbations that would transform them into spheroidals, because dramatic tidal forces and repeated harassment are less common. That doesn't mean void galaxies never change shape, but it can tilt the balance toward preserving disk structures over long timescales. Void galaxies can still host active galactic nuclei, because AGN activity depends largely on whether gas finds its way into the central black hole. However, luminous AGN are often studied more in denser survey regions simply because there are more galaxies there, so large statistical samples are easier to gather, making void AGN comparatively less common in many catalogues. The Boötes Void has been used as a case study for whether environment primarily drives galaxy formation or mostly modifies it, because its extreme low-density setting reduces many external bead influences. By studying what changes and what stays similar compared to galaxies in filaments and groups, researchers can infer which galaxy properties are strongly environment-dependent and which are more universal. The existence of starbursts within a void supports the idea that internal and small-scale processes can dominate in some cases. Because a galaxy can still experience instabilities, gas inflow, or minor interactions, even without living in a crowded region. This shows that environment matters does not mean environment controls everything, but rather that multiple pathways can lead to similar galaxy behaviors. Void galaxies also help test models of gas inflow, feedback, and star formation thresholds in shallow potential wells, especially for smaller galaxies. In low-mass halos, a burst of star formation can blow gas outward more easily, and the ability to reaccrete fresh gas can be strongly influenced by the surrounding density, making void settings a valuable berets. Comparison point for theoretical models. Voids can be characterized by a radial density profile, describing how the density changes from the center outward to the edge, which helps quantify the structure more precisely than a simple empty/not pow. Empty label. Typically, the interior is the most underdense, and density rises toward the boundary, sometimes even forming a mild ridge where matter has accumulated. Some analyses refine void profiles by adding galaxies found in infrared catalogs that were missed in optical samples, highlighting how detection methods influence the measured structure. Including infrared-selected galaxies can increase counts inside and near the void, altering the inferred profile and making the boundary appear smoother or differently shaped. A void's effective radius is often defined as the radius of a sphere that would have the same volume as the actual void region, even if the real shape is irregular. This is a convenient way to compare voids of different shapes and sizes, because it translates complex geometry into a single representative number. In large surveys, voids are often binned by effective radius, so researchers can compare average properties of small, medium, and large voids. This approach helps reveal trends, such as whether larger voids have steeper density gradients, different galaxy populations, or different lensing signals compared with smaller ones. The number of galaxies inside a void depends strongly on whether you count only bright galaxies or include dwarfs, because dwarfs can be numerous, yet difficult to detect. bright galaxies are easier to map at large distances, but dwarfs can dramatically change the population picture once surveys become deep enough to find them reliably. Early popular summaries often emphasized emptiness by comparing expected bright galaxies with observed bright galaxies, which created a dramatic and memorable contrast. That framing is useful for intuition, but it can also oversimplify, because it makes the void sound like a near-perfect vacuum when, in reality, deeper surveys can reveal many faint members. Later work clarified that empty in cosmology typically means underdense by a large factor, not literally empty, because matter is never completely absent on these scales. Even the emptiest voids contain dark matter, tenuous gas, and some galaxies, and the key scientific point is the reduced density relative to the cosmic average. In cosmic web language, voids are often said to occupy most of the volume, filaments most of the mass, and clusters the most concentrated luminous matter, capturing a broad geometric and physical summary. This helps explain why the universe looks structured. The visible light is concentrated into small, dense regions, while the vast majority of space is taken up by underdense expanses. A large void can be bounded by multiple superclusters and filaments, producing a kind of foam-like or honeycomb arrangement in some reconstructions. In this picture, superclusters and filaments form the brighter walls and corners, while the void is the interior cell, giving the cosmic web its characteristic large-scale texture. The Boötes Void is often used in teaching as a vivid example of how redshift surveys revealed the cosmic web, because its scale and history make the concept easy to illustrate. It shows how mapping galaxies in 3D transformed astronomy. What looked like a scattered pattern in the sky became a structured network with huge gaps, walls, and filaments once distances were measured. A practical reason voids are studied is that their low-density interiors reduce environmental noise when examining intrinsic galaxy properties, making it easier to isolate what a galaxy does, mainly because of its own mass and internal physics. In crowded regions, galaxies are constantly being nudged, stripped, or merged, so it can be hard to tell whether a trait comes from the galaxy itself or from repeated outside influences. In voids, many of those strong influences are weaker, allowing clearer comparisons. Another reason voids matter is that their shapes can respond to cosmological geometry, which means they can potentially be used in methods that act a bit like standard rulers. If you have a population of voids with typical statistical shapes, you can compare how they appear along and across the line of sight. And that comparison can carry information about distances and expansion, though it requires careful modeling and large datasets. Void galaxy alignment studies explore whether galaxy spins and shapes correlate with nearby filaments and walls, because galaxies are not formed in isolation from the cosmic web. The large-scale gravitational field can gently torque forming galaxies and their halos, potentially leaving subtle alignments between a galaxy's orientation and the structure around it. These alignment patterns can test theories of tidal torque and the role of large-scale shear fields, which are ideas about how gravity in the early universe twists matter as structures grow. If galaxies form inside halos that are being shaped by the surrounding web, their angular momentum may carry a faint imprint of that environment, and voids provide a distinct setting to look for those imprints. The internal dynamics of voids are sometimes approximated as expanding regions embedded in an expanding universe, a useful simplification for understanding how matter moves. In this picture, the universe expands everywhere, but voids can expand a bit more relative to average, because their lower density means less gravitational pull to slow the expansion locally. In some analytic approximations, void evolution is described as a kind of mirror image of overdensity collapse. Overdense regions slow down, turn around, and collapse, while underdense regions thin out and expand. It's not a perfect symmetry, but it helps build intuition clusters become denser and smaller relative to the background, while void interiors become more rarefied and larger. As voids grow, surrounding walls can become thinner and more pronounced, because matter that leaves the void doesn't vanish, it accumulates at the boundaries. Over long cosmic timescales, this process can sharpen the contrast between the emptiest interior and the denser edges, making the cosmic web's foam-like appearance more distinct in maps. The Boötes Void helped motivate searches for emission-line galaxies because star-forming systems were thought more likely to be missed in bright, broadband catalogues. Emission-line galaxies can stand out even when their overall starlight is faint, so they became a natural target when astronomers wanted to test whether the void was truly empty or simply missing certain types of team. Galaxies in older samples. Objective prism techniques disperse light so that strong emission features become easier to spot across wide areas of sky, allowing efficient discovery of candidates. Instead of taking detailed spectra one object at a time, this method can highlight many potential emission line sources quickly, which is valuable when you're searching for rare galaxies in a large volume. Some void galaxy surveys emphasized spectroscopy because photometric selection alone can't reliably assign true 3D position. A galaxy may look like it sits inside of the void in a photograph, but only a measured redshift can confirm that it actually lies at the void's distance rather than being in the foreground or background. The Boötes Void is not the same object as the Boötes supervoid, sometimes discussed in cosmic microwave background contexts, and naming can vary by the specific study and definition. This is a common source of confusion. Different researchers may use similar sky directions or overlapping underdense regions, but the precise volumes, redshift ranges, and scientific contexts can be different. Astronomical naming can be confusing because different surveys can label overlapping underdensities differently, especially as maps improve. As new data reveals finer structure, what once looked like one large empty region may be subdivided into several voids, or several underdense regions may be grouped together, changing names and boundaries over time. A void's central coordinate is often a convenient reference rather than a perfectly defined physical center, because real voids are not perfectly symmetric. Since the density varies gradually and the boundary is irregular, the center is often chosen as the point of minimum density, or as a best-fit geometric center useful for consistency, but not a rigid physical marker. The Boötes Void's historic coordinate is widely repeated because it was the reference used in early survey papers and summaries, and those became widely cited. When an object becomes famous in the literature, the original reference coordinates often stick, even as later analyses refine details, because they provide a stable anchor for discussion. Galaxy redshift surveys in the 1980s required extensive observing campaigns compared with today, often measuring spectra for galaxies with far less automation. Building a 3D map then meant painstakingly collecting redshifts object by object, so identifying a giant void from those efforts was especially striking and helped show the value of systematic mapping. Modern surveys can collect thousands of spectra per night using multi-object instruments, enabling far denser sampling of the cosmic web. With so many more measured redshifts, astronomers can build detailed void catalogues, identify smaller filaments within underdense regions, and compare void populations across large swaths of the sky. As sampling improves, the sharpness of a void boundary can change, because faint galaxies and thin filaments that were previously invisible begin to appear. This doesn't mean the void disappears. It means our picture becomes more detailed, revealing that empty regions often contain subtle structure that only shows up with deeper data. For that reason, a named void from early literature can become less empty as datasets improve, while still remaining an underdensity compared to the cosmic mean. The core idea stays the same. The region has fewer galaxies than average at that scale, but improved surveys reduce how extreme the emptiness appears by uncovering fainter members. Void interiors are often described as having a shortage of L** galaxies, roughly Milky Way-like luminous galaxies, rather than a complete absence of dwarfs. This is an important nuance. Bright galaxies are the easiest markers of structure, and their scarcity makes a void stand out strongly, even if many faint galaxies still exist below earlier detection limits. This distinction matters because dwarf galaxies can dominate the number counts, while contributing much less total light and mass compared with bright galaxies. So a void can contain many dwarfs, yet still look empty in a bright galaxy map. And the scientific interpretation depends on whether you're measuring luminosity density, number density, or underlying matter density. Some Boötes region studies compare void galaxies to field galaxies to isolate environmental effects, because field galaxies provide a more typical baseline than cluster galaxies. The goal is to compare galaxies that are not in rich clusters, but also not in the deepest underdensities, to see what changes as you move from average environments into truly sparse ones. Field galaxies usually means galaxies outside rich clusters, but many still live in filaments or loose groups that have near-average density compared to void interiors. So field environments can include moderate interactions and normal web connections, making them a helpful intermediate point between the extremes of clusters and void cores. That's why E-void versus field comparisons test a subtler contrast than cluster versus field comparisons, focusing on what changes when you go from ordinary cosmic web living to the most underdense environments. These comparisons can reveal whether differences are dramatic or modest, and which galaxy properties are most sensitive to large-scale density. In void interiors, local galaxy density can be far below the cosmic mean, which changes neighbor statistics in a very direct way. Fewer neighbors means fewer close gravitational encounters, fewer chances of strong tidal stripping, and fewer mergers, all of which are major drivers of galaxy transformation in denser regions. Neighbor statistics influence how often galaxies experience close passes that can funnel gas inward, disturb disks, or trigger new star formation. In a sparse environment, those triggering events occur less often on average, which can lead to slower morphological evolution and different distributions of star formation histories across the galaxy. Population. A galaxy can be inside a void by large-scale definition and still have a close companion, especially in small internal associations. This is a reminder that environment has layers. A galaxy can be in an underdense region relative to the cosmic mean, while still being in a small local pair where interaction physics matters. Some H1 studies explicitly discuss companions to known void galaxies detected in radio observations, because neutral hydrogen can reveal faint neighbors that are hard to see optically. Discovering such companions helps clarify whether a void galaxy is truly isolated or part of a small interacting system hidden from earlier optical surveys. These companions indicate that small-scale clustering can exist within large-scale underdensities, which is fully compatible with cosmic structure formation. The universe can be sparse on hundreds of megaparsec scales while still producing small pairs and triplets on much smaller scales, since local gravitational collapse can occur even when the broader region is underdense. In many models, void interiors have lower external pressure from surrounding gas, which can influence how galactic winds propagate. When a galaxy drives outflows through supernova and stellar winds, those outflows push against the surrounding medium in a lower density environment. The outflow can expand more easily and travel farther before slowing. Because the ambient density is lower, outflows can spread more freely, potentially affecting how metals are distributed around void galaxies. Metals produced in stars can be carried outward by winds, and in a sparse setting, they may pollute a larger surrounding volume, changing the chemical environment of the galaxy's outskirts and nearby intergalactic space. Void galaxies are useful for studying cold gas fractions because reduced stripping processes allow extended H1 disks to survive longer. In dense regions, external forces can peel gas away or heat it, but in voids, the gentle environment can preserve large, calm reservoirs of neutral hydrogen around galaxies. Large H1 reservoirs can sustain star formation over long timescales, even if the current star formation rate is modest, because the fuel supply remains available. A galaxy doesn't need to be in a starburst to be active over cosmic time. A steady, low-level conversion of gas into stars can continue for billions of years if the gas is retained and replenished. Some spectroscopy of Boötes Void galaxies focused on emission lines tracing ionized gas in star-forming regions, because those lines provide direct evidence of ongoing stellar birth. They also help estimate star formation rates, gas conditions, and the dominant energy sources shaping the galaxy's spectrum. Emission line widths can provide kinematic information about gas motions and rotation, offering clues about galaxy mass and internal dynamics. Broader lines can reflect faster rotation or more turbulent gas, and by measuring these features, astronomers can connect void galaxy properties to the gravitational influence of their dark matter halos. Void environments can test whether scaling relations, such as the Tully-Fisher relation between rotation speed and luminosity, differ at very low density. If environment had a strong effect on fundamental galaxy structure, these relations might shift. If the relations hold, it suggests many galaxy properties are governed primarily by internal mass and dynamics. Many studies find that broad galaxy scaling relations are surprisingly robust across environments, with changes showing up more in the distribution of galaxy types than in the basic relations themselves. In other words, a void may contain more gas-rich disks and fewer quenched spheroidals, but the underlying physics linking mass, rotation, and luminosity can still look similar. That robustness supports the idea that halo mass and internal physics dominate many galaxy properties, while environment acts as a secondary modifier that changes probabilities rather than rewriting the E. Fundamental rules. It suggests that a galaxy's core behavior may be set largely by its mass and gas, while the environment influences how often certain events like mergers occur. Even so, some analyses find that void samples show higher specific star formation rates at fixed mass, meaning that, compared to similar mass galaxies elsewhere, void galaxies may be forming stars more actively relative to their size. This can reflect differences in gas availability, fewer quenching interactions, or a different balance of inflow and feedback. Specific star formation rate measures star formation rate per unit stellar mass, which is a way to describe how quickly a galaxy is growing compared to the stars it already has. A higher value means the galaxy is building up its stellar population more rapidly relative to its current mass, often associated with younger stellar populations or more available cold gas. Differences in specific star formation rate can arise from differences in gas supply, feedback strength, or star formation efficiency, and voids offer a clean environment to explore these possibilities. In a sparse region, a galaxy might keep its gas longer, accrete gas more smoothly, or experience fewer disruptive events, any of which can shift how actively it forms new stars. Cosmological simulations often show void galaxies accreting gas more smoothly, with fewer disruptive events, because they live away from the busiest crossroads of the cosmic web. This smoother growth can lead to calmer star formation histories and more stable disk structures over long timescales. Smooth accretion can sustain extended disks and ongoing star formation without needing many merger-driven starbursts, providing a pathway for galaxies to grow steadily. In this picture, a galaxy's evolution is less about dramatic collisions and more about persistent, gentle feeding from the surrounding intergalactic medium. At the same time, the presence of extreme starbursts in void samples implies that internal instabilities or minor interactions can still create bursts, even without major mergers. A small companion, a gas inflow event, or a disk instability can compress gas and ignite rapid star formation, showing that bursts have multiple possible triggers. Void galaxies can be used to study how reionization feedback affected low-mass halo formation in underdense regions, because underdense areas can have different timing in structure growth. Reionization heated intergalactic gas in the early universe, and that heating made it harder for the smallest halos to hold onto gassy void environments, can reveal how those effects played out where structure formation was slower. Underdense regions can have delayed structure formation compared with overdense regions, shifting typical halo assembly times later. That means galaxies in voids may, on average, assemble their mass and form stars on different schedules, not because the laws of physics change, but because the available matter and gravitational environment evolve differently. This delay can influence stellar ages and chemical enrichment for some void dwarfs, potentially leaving them with younger average stellar populations or different metallicities compared with similar mass dwarfs in Chendi, denser areas. The idea is not that all void dwarfs are young, but that the environment can tilt the statistical trends in formation history. Observationally, measuring stellar population ages in faint void dwarfs is challenging because these galaxies are dim, diffuse, and distant. Their light can be hard to collect in enough detail to separate stellar populations precisely, so such measurements often require long exposures, large telescopes, or careful multi-wavelength analysis. Multi-wavelength data helps because ultraviolet traces recent star formation, optical light captures a broader range of stellar ages, and radio maps cold gas that may fuel future stars. By combining these views, astronomers can build a more complete picture of how void galaxies live, how much gas they have, how actively they form stars now, and what their longer-term history might be. Large named voids like Boötes are often targeted for follow-up because their direction is well known and historically mapped, making them convenient laboratories. A famous void gives researchers a shared reference point, so different teams can compare results more easily and test methods in a region with a long observational history. The story of the Boötes Void is often used to show how mapping the universe required moving from 2D sky patterns to 3D redshift catalogs, because the void is not obvious in a flat image of the sky. Only when distance is added does the structure appear clearly, revealing that the universe is organized into walls and gaps, rather than a simple random sprinkle. In the cosmic web picture, matter flows from voids toward walls and filaments, and from filaments into clusters, following the pull of gravity. This flow is slow on human timescales, but profound over billions of years, shaping where galaxies form, where gas accumulates, and how the largest structures become more pronounced. This flow pattern is driven by gravity acting on tiny initial density fluctuations that grew over cosmic time, turning subtle early differences into the large-scale web we observe today. The universe began extremely uniform, but not perfectly so, and those tiny differences were enough for gravity to sculpt the vast pattern of crowded filaments and spacious voids. The amplitude of those initial fluctuations is measured in the cosmic microwave background, linking void statistics to early universe physics. By studying the large-scale distribution of voids and filaments, cosmologists can connect what they see now to conditions measured in the oldest light in the universe, creating a coherent story from the early Papa, cosmos, to today. Because voids evolve differently from clusters, Combining void and cluster information can help break cosmological parameter degeneracies, meaning it can help distinguish between different cosmological bow, explanations that might otherwise look similar. Clusters probe the overdense regime, voids probe the underdense regime, and together they offer a more complete test of how structure grows. Void shapes can be distorted by redshift space effects, and by modeling these distortions, researchers can infer growth rates of structure. The key idea is that peculiar velocities alter how voids look in redshift maps, and those velocity patterns depend on gravity and cosmic expansion, so careful modeling turns the distortion into a measurable signal. Some methods treat voids as quasi-spherical and look for anisotropies to test cosmological geometry, similar in spirit to Orkoc-Peczynski-type tests. If the assumed cosmology is wrong, a statistically spherical population can appear squashed or stretched along the line of sight, so measuring that distortion can help constrain distance-redshift relationships. Voids are also used in studies of galaxy bias, because galaxies trace the underlying matter field imperfectly, and that relationship can change in underdense regions. Bias describes how galaxy density relates to matter density. Voids provide a regime where matter is sparse, letting researchers test whether the same bias relationships hold as in average or dense environments. Bias can be scale-dependent, and voids probe a different density regime than clusters, providing complementary information about how galaxies populate halos across the cosmic web. By comparing how galaxies behave in both extremes, researchers gain a fuller picture of the connection between visible structure and the invisible dark matter framework. Void catalogs can be built from galaxy distributions, from dark matter and simulations, or from reconstructed density fields, and each approach captures a slightly different view of the same underlying tableau. Reality. Galaxy-based voids trace where light is scarce. Simulation-based voids trace where mass is scarce, and reconstructions try to infer the mass field from observed galaxies and dynamics. Each construction method yields voids with somewhat different physical interpretations and systematic uncertainties, because each method depends on data quality and modeling assumptions. That's why modern void studies often compare multiple catalogs and methods, looking for results that remain stable across approaches. The Boötes Void was initially described as empty, largely because it lacked the bright galaxies common in surrounding regions, which made it stand out strongly in early maps. Bright galaxies serve as obvious markers of structure, and their absence creates a dramatic visual and statistical signal, even if faint galaxies remain undetected. Over time, surveys identified more galaxies within its boundaries, reducing the apparent emptiness without erasing the underlying underdensity. This is a natural outcome of improving data. As detection thresholds fall, more faint members are found, and the void becomes understood as very underdense rather than nearly nothing at all. Some compilations describe several dozen to around 60 known galaxies in the void, depending on how the void is defined and how deep the census goes. That range highlights that void membership is not a single fixed list. It changes as surveys improve and as researchers apply different boundary criteria. A key lesson from Boötes is that apparent holes in galaxy maps are not automatically data errors. They can be real cosmic structures. The universe is genuinely structured, and an empty-looking region can be an authentic feature of the large-scale matter distribution rather than a missing patch of observations. Another lesson is that mapping large-scale structure requires careful statistical expectations for how many galaxies should appear in a given volume. You need a baseline. What would normal look like for the survey's depth and selection? Once you have that baseline, a large deficit becomes meaningful evidence for a true void. Early redshift surveys often used wedge diagrams to visualize galaxy density versus distance and angle, turning vast data sets into understandable pictures. These POTS made it possible to see filaments, clusters, and voids at a glance, helping astronomers recognize that galaxies trace a web-like pattern rather than filling space evenly. Those wedge diagrams made it visually obvious that galaxies cluster into arcs and walls, leaving large interior gaps, which is essentially the signature of voids. The cosmic web became not just a theory, but something you could see in the data. Thick lines and clumps of points surrounding wide, quiet spaces. The Boötes Void appears as a prominent gap in certain sky directions when plotted in these diagrams, making it a striking teaching example. Seeing a broad, empty wedge helps people understand that a void is not a single empty point, but a large volume where the density stays low across a wide range of distances. The void's existence contributed to a shift away from thinking of galaxies as randomly sprinkled on these scales, because the pattern was too organized and too extreme to be explained by simple randomness. Instead, it pointed toward a universe where gravity had sculpted matter into interconnected structures with significant empty volumes between them. The cosmic web paradigm now treats voids as essential components rather than exceptions, because voids are the natural counterpart to filaments and clusters. You cannot fully describe the universe's structure without describing where matter is scarce, since those underdense regions shape the geometry and evolution of everything around them. Star formation in void galaxies can be traced by hydrogen recombination lines, ultraviolet emission, and infrared dust emission, each highlighting a different part of the process. Recombination lines reveal ionized gas around young stars, ultraviolet reveals the hot light of those young stars directly, and infrared reveals the dust warmed by that starlight together, giving a fuller cast. Picture of star-forming activity. Neutral hydrogen content is traced by the 21 centimeter line and can reveal extended gas disks beyond optical radii, showing that galaxies can have large reservoirs of fuel, invisible in BR. Starlight. In voids, where stripping is weaker, these extended gas structures can be especially informative for understanding how galaxies retain and use their gas. Some void galaxy surveys emphasize dwarf galaxies because dwarfs are more sensitive to environment and feedback, making them good test particles for theory. A small change in gas supply or heating can have a large effect on a dwarf's ability to form stars. So dwarfs help reveal environmental influences that might be subtle in massive galaxies. Void dwarfs can test whether star formation shuts down more easily in low-mass halos when gas accretion is reduced, because in underdense regions, fresh gas supply might be lower or more delayed. If dwarfsing voids look systematically different from dwarfs elsewhere, it can inform models of how gas flows and feedback operate in the smallest galaxies. On the other hand, void dwarfs can also test whether reduced harassment allows them to retain gas longer than similar dwarfs in groups, because fewer close encounters can mean fewer tidal disturbances and less cowl. Stripping. This sets up an interesting tension. Voids might provide less new gas, but they might also remove less existing gas, and observations help determine which effect dominates. Surveys of emission-line galaxies toward Boötes show that at least some void galaxies are actively forming stars today, because strong emission lines are direct signatures of energetic young stellar populations. This demonstrates that life inside a void can still be dynamic and ongoing, even if the region is globally underdense. The label "extreme starburst" in Boötes Void samples indicates unusually strong star formation signatures for certain galaxies, suggesting intense, concentrated episodes of stellar birth. These galaxies stand out because their emission lines and other indicators imply rapid conversion of gas into stars, sometimes far above what is typical for galaxies of similar mass. The presence of such starbursts suggests that local triggers like small companions, minor interactions, or internal instabilities can, be sufficient to ignite rapid star formation. Even in a sparse region, a single close neighbor or a sudden inflow of gas can compress material and spark a powerful burst, showing that dramatic events can occur without a crowded environment. Some studies have searched for X-ray signatures of void galaxies, which can indicate hot gas, energetic stellar remnants, or active galactic nuclei. X-rays can come from matter heated to very high temperatures, from black hole accretion, or from populations of X-ray binaries, so finding X-ray emission helps identify energetic processes that might not be obvious at other wavelengths. X-ray samples in voids are often small because most void galaxies are not strong X-ray emitters compared with rich clusters, where huge amounts of hot gas glow in X-rays. Still, even a small sample is useful, because it helps clarify what kinds of high-energy phenomena occur in the most underdense environments. The Boötes Void shows that empty regions still require diverse survey strategies to detect faint and atypical galaxies, because no single method finds everything. Optical surveys may miss low surface brightness galaxies, infrared surveys highlight dust and star formation, and radio surveys reveal neutral gas, each one contributing a different piece of the full Crete population. Each wavelength band has its own selection bias. Optical emphasizes starlight, infrared emphasizes dust and star formation, and radio emphasizes neutral hydrogen. Knowing these biases helps astronomers interpret void galaxy counts correctly, because differences in detected populations can reflect the survey method as much as the true cosmic distribution. Using multiple bands reduces the chance that a void is artificially empty due to missing a particular galaxy population, making conclusions more robust. If a region looks underdense across optical, infrared, and radio selections, confidence rises that it's a genuine underdensity rather than a quirk of one survey's limitations. The Boötes Void also demonstrates how scientific interpretations evolve as deeper datasets become available, often shifting from dramatic early impressions to more nuanced, quantitative descriptions. Early on, the focus might be, it's astonishingly empty, while later the focus becomes, what is the density profile? What types of galaxies exist there? And how does it compare statistically to other voids? Early public narratives emphasized near emptiness, whereas later technical work often emphasizes density profiles and comparisons to other voids of similar size. This evolution reflects how science refines. Initial discoveries highlight the most striking features, and later work measures details, boundary definitions, and population characteristics. Some summaries suggest that Boötes is broadly consistent with typical void characteristics found in later surveys, meaning it fits within the expected range of void behavior in standard cosmology. This doesn't make it uninteresting. It makes it valuable as a classic example of a phenomenon that is now understood as a natural part of cosmic structure. This typicality does not mean the void is small. It means that large voids can arise naturally in Lambda Cdem and appear in both simulations and observations. Boötes is still enormous. Its importance is that it helped reveal the cosmic web early, and its properties align with what later, larger surveys showed to be common. Named voids are often less useful scientifically than large void samples, because statistics require many objects to average out randomness and measurement noise. A single void can be influenced by local peculiarities, but an ensemble allows researchers to extract general laws and trends about void sizes, shapes, and galaxy populations. Even so, a named void like Boötes is very useful for targeted studies and for communicating the concept of voids clearly, because it provides a concrete, well-known reference. Having a famous example makes it easier for researchers and learners to talk about methods, histories, and results in a shared context. Boötes remains one of the best-known voids because its discovery coincided with the rise of modern redshift mapping, so it became linked with a turning point in how we see the universe. It stands as a reminder of when the universe shifted, in our understanding, from a scattered sky of points to a structured 3D landscape. The Boötes Void is an example of a low-density region that helped validate how lumpy the universe is on scales of hundreds of megaparsecs. Seeing such a large underdensity supported the growing realization that matter is strongly patterned at these scales, with big contrasts between dense nodes and sparse interiors. Its study contributed to broader acceptance that galaxy distribution is highly non-uniform on intermediate scales, and that this non-uniformity has a coherent structure rather than random patchiness. The cosmic web concept became a natural explanation for what redshift surveys were revealing across many directions and distances. Over sufficiently large scales, cosmology still expects the universe to be statistically homogeneous, meaning that if you average over vast enough volumes, the density smooths out. Large voids do not contradict this, because homogeneity is a statistical statement about very large averages, not a claim that every region is identical. The existence of large voids is compatible with statistical homogeneity because underdensities are balanced by overdense filaments and clusters, and the overall average remains consistent. Voids and walls are two sides of the same structure. Matter moved, but it stayed within the universe, creating contrast without breaking the large-scale averages. Voids provide complementary cosmological tests because they probe the underdense regime that clusters do not, offering a different sensitivity to the laws governing expansion and gravity. Clusters test how matter collapses under gravity. Voids test how matter evacuates and expands together, giving a more complete picture of structure growth. The Boötes Void is frequently referenced when discussing how voids were first recognized observationally, because it is a historically clear case where redshift data revealed a large-scale gap. It shows how a careful mapping approach can uncover cosmic structure that is invisible in simple sky images. The combination of methods used: redshift surveys, emission line searches, eras selections, and H1 mapping demonstrates the multi-tool nature of large-scale structure research. Each method answered a different question. Where are galaxies missing? What types might be hidden? How much gas is present? And what kinds of activity occur within the underdensity? Cumulative Boötes research shows that void galaxies can include normal star-forming disks, dwarfs, and occasional starbursts, rather than being limited to a single void galaxy stereotype. The environment is unusual, but the galaxies can span a range of types, with trends that emerge statistically rather than absolute rules. It also shows that void boundaries are scientific constructs dependent on data quality and definitions, because the transition from underdense to average density is gradual and irregular. As surveys improve, the outlines shift slightly, and the most accurate picture becomes a probabilistic one: density fields, profiles, and gradients, rather than a hard edge. The Boötes Void continues to be cited as a dramatic early example in reviews of void structure and dynamics, partly because it has a long history of study and because it remains intuitively compelling. It serves as both a scientific case and a teaching anchor, connecting early mapping efforts to modern void science. Void studies often distinguish between void-in, void evolution, where small voids merge and grow, and void-in cloud evolution, where small voids can be crushed by surrounding overdensities. This distinction helps explain why some underdense regions survive and expand, while others are eventually overtaken by nearby collapsing structures. Large, mature voids are typically of the void-in-void type, expanding within already underdense surroundings, which allows them to grow over cosmic time. In that scenario, the environment supports continued evacuation and expansion, enabling the development of the largest voids seen in the cosmic web. The Boötes Void scale made it an early example consistent with void-in-void growth narratives, offering a plausible framework for how such a large underdensity could develop. While the exact history depends on surrounding structures, the general concept fits. Emptier regions can merge and deepen as the universe evolves. Voids can show a compensation ridge, where density slightly overshoots the mean near the boundary because evacuated matter piles up at the edges. This is like a subtle ring around a bubble. Matter leaving the interior contributes to a denser shell, which can sometimes appear as a ridge of galaxies and higher matter density around the void. Measuring such ridges observationally requires dense sampling of galaxies around the void edge because the signal is statistical and the boundary is irregular. If galaxy coverage is sparse, the ridge can be hard to detect reliably, so modern surveys with large, uniform samples are especially helpful for this kind of measurement. The Boötes Void's edge regions are where filaments and superclusters are most likely to appear in maps, because the boundary is where matter has accumulated. This creates a natural contrast. The interior is sparse, while the edges connect into the broader network of filaments that link clusters and superclusters. Void edges can host galaxy transformations more often than void interiors, because interactions become more frequent as density rises. As you approach the boundary, galaxies have more neighbors, more chances for tidal encounters, and more access to flowing gas along filaments, which can change star formation rates and morphologies compared to the quiet interior. These gradients in galaxy properties can be studied by comparing galaxies at different distances from void centers, turning the void into a kind of natural experiment. By seeing how galaxy color, gas content, star formation, and morphology change from center to edge, researchers can quantify how environment influences evolution across a continuous density range. Void galaxies can also be compared with filament galaxies to isolate intermediate environment effects, not just extremes. Filaments represent the normal highways of the cosmic web, where gas and galaxies are more common. Comparing them to void interiors helps pinpoint what changes specifically when galaxies are cut off from the busiest parts of the web. Such multi-environment comparisons help determine whether observed changes are driven by local density, halo mass, or large-scale tidal fields, because different factors can correlate but are not identical. Careful studies try to separate these influences, asking whether a galaxy behaves differently mainly because of where it lives, or because of what kind of halo it sits in, or because of the gravitational shape of its surroundings. The historical narrative of the Boötes Void includes a shift from astonishingly empty to a large, deep but explainable underdensity as surveys advanced and theory matured. This is a natural arc of scientific understanding. First, the surprise of discovery, then the steady refinement that places the object within a broader framework. The void's existence reminds us that the universe contains both extreme overdensities and extreme underdensities, and that both are expected outcomes of structure formation. The cosmic web is defined by contrast-dense clusters and superclusters on one side, and expansive voids on the other. The underdense regime is crucial for testing theories because physical processes can behave differently when matter is sparse, especially for subtle gravitational effects and for how galaxies acquire or lose gas. By studying the quietest regions, researchers can test whether standard physics describes both crowded and empty environments consistently. The Boötes research shows that identifying faint galaxies often requires targeted follow-up, rather than relying only on general-purpose catalogues, because rare environments demand deeper and more specialized searches. When the object of interest is what's missing, you need especially careful tools to ensure you are not mistaking observational limits for true emptiness. It also shows that empty regions are scientifically rich, because rarity itself constrains models of how structure forms and evolves. If a void is too large or too empty compared with what a model predicts, that tension would matter if it matches predictions. It strengthens confidence that the model captures the universe's large-scale behavior. Large voids are now routinely seen in both observations and simulations, supporting the idea that they arise naturally from gravitational evolution acting on early fluctuations. This convergence between what is mapped in the sky and what appears in simulated universes is one of the strongest reasons voids are viewed as expected components of cosmology, rather than mysteries. The Boötes Void remains widely referenced in educational and popular discussions because it is a clear, dramatic example of a cosmic void, and because its story is tightly linked to the development of 3D mapping. It helps people grasp that the universe is not just a collection of galaxies, but also a structure of vast spaces between them. Its study spans decades and multiple methods, illustrating how observational cosmology builds confidence through independent lines of evidence. When different techniques, optical redshifts, infrared selection, radio gas, serve as a point toward the same underdense conclusion, the overall picture becomes much more reliable. The Boötes Void is a vivid example that cosmic structure is defined both by where galaxies are and where they are not. The negative space is not an afterthought. It is part of the same gravitational story, showing how matter moved, gathered, and left behind immense, low-density volumes. As redshift mapping progressed from early pencil beam surveys to wide field surveys, the Boötes Void moved from being a startling discovery to a standard reference point for understanding voids. And as you sit with that idea of a universe shaped into filaments, walls, and wide, quiet regions, you can simply let the scale of it soften into the background, like distant starlight, steady and unhurried. Everything continues to expand and drift,